The diagram depicts a dual-core ARM application that featuring A53 and R5 cores. The first core is A53 that runs a FreeRTOS application and controls the first LED. It reads the state of first push button through an AXI GPIO interface in polling mode. When the push button is held, the A53 core starts blinking the first LED by sending pulse signals over the AXI GPIO interface. It also prints Hello World from A53 on serial terminal. The second core is Cortex R5. It operates as a standalone processor, and it controls the second LED similarly by monitoring the second push button. When the second push button is pressed, the R5 core starts blinking the second LED. It prints Hello World from R5 on serial terminal as long as the push button is held. AXI Interconnect connects the AXI GPIO peripherals to the high-performance master port 0, which is shared by both ARM cores. This setup allows the cores to send and receive AXI transactions toward the GPIO interfaces. The DDR memory is partitioned into two regions, one for each core. This avoids memory contention and ensures that both cores operate independently without interfering with each other. Let's start Vivado and make the complete block design. First, add the Zynq UltraScale plus IP. You'll see a banner appear at the top of the diagram, suggesting to run block automation. Click on Run Block Automation, select Apply Board Preset, and click OK. This process configures the IP with preset parameters that match the evaluation board layout. Add an AXI GPIO to the block design to control the first user LED. Set the direction to all output and configure the bit width to 1 bit. Rename it to ARM0 LED Control. This naming is only for better recognition, and you can choose any desired names. Expose the AXI GPIO output as an external port. Rename the created port to ARM0 LED pin. Next, add another AXI GPIO for reading the first push button. Set its direction to input and configure its bit width to 1 bit. Rename it to ARM0 switch for easier understanding. Make the input as external port and rename the port to ARM0 switch pin. Now we need to repeat the job to add two other AXI GPIOs and connect them to next push button and LED. Add another AXI GPIO and make it as 1-bit output. This time use ARM1 during the renaming process. Another AXI GPIO will be as 1-bit input to read the second push button in polling mode. These two AXI GPIOs will be used with R5 to blinking the LED while the push button is held. Since we only need one HBM port, open the Zynq IP and deselect second master HBM port. Auto connection. At this point, we can let Vivado handle the connections automatically. Run the connection automation feature. This will automatically add a processor system reset and an AXI interconnect to the design. Validate the design. Once the design is validated, Vivado will automatically assign addresses to the AXI GPIOs. Let's have a look at the address editor. Later we can use these addresses in Vitis to access the GPIOs by MMIO method. Add top wrapper to your design, and then you can proceed to synthesis the design. Assigning the I/O ports. Open Synthesize Design and Open I/O Ports window. Assign the LED pin and push button for first ARM cores peripherals. Based on your evaluation board, assign the appropriate pins for the LED outputs and push button input. Repeat the job for dedicated LED and push button for ARM Core 1. Once the pins are assigned, save your I/O connections as an XDC file. If you're working with the ZCU104, I've also shared a pre-configured XDC file in the GitHub repository for convenience. With everything set, you're now ready to generate the bitstream. From the left-hand toolbar, select Generate Bitstream and wait for the process to complete. Exporting the hardware. The last step in Vivado is to export our hardware design for use in Vitis. Go to File, Export, Export Hardware, and make sure to check the Include Bitstream option. Part 2 Vitis Project. Launch Vitis IDE and create a new application project. When prompted, select the XSA file exported from Vivado and create a new platform. For the boot component, select Zynq MPSoC FSBL to set up the initial boot process for the device. Choose a name for your project. When we are creating new platform, it will set up the application properties for first ARM core. Therefore, for the next steps, configure the platform to support FreeRTOS running on the A53 core. Since the first application will run on the A53 core, select FreeRTOS as the operating system. Next, select an empty C application from the provided templates. This process will create our first application project. Download the provided C files from the GitHub repository, copy the A53 main file, and paste it into the source folder of the project. The driver code includes key sections such as address definitions and pushbutton control. Address definitions are defined as macros for the base addresses of the two AXI GPIOs dedicated to the A53 core. These macros are derived from the X parameters header file and correspond to the hardware design in Vivado. In the pushbutton control section, the program reads the state of first pushbutton in polling mode. When the pushbutton is pressed, the program toggles the first LED and prints "Hello World" to the terminal. Please note that the AXI GPIO peripherals are accessed using ZIL in and ZIL out. A 25 millisecond delay is added to ensure the LED blinking frequency is visible. Once the application is ready, build the project. After the build is completed, the first ELF file will be generated for the A53 core. Create a new domain. To run another application on the R5 core, we need to create a new domain in the platform. Open the platform SPR by double-clicking it. You will see the existing FreeRTOS domain for the A53 core. Right-click on the platform and select Add Domain. Provide a name for the new domain, and from the OS drop-down, select Standalone as the operating system for the R5 core. From the processor drop-down, choose Cortex R50 and click OK. The platform will now be outdated. Build a platform to update it with the changes. Second application. Add a second application by right-clicking on the application project and selecting Add Application Project. Provide a name for the new application. In the application wizard, select Cortex R50 as the target processor. Since there is only one domain created for the R5 core, it will be automatically selected. Choose an empty C application from the templates and complete the wizard. Copy the main file for the R5 core from the provided resources and paste it into the source folder. The main file has a similar structure to the A53 driver, but it uses base addresses of the third and fourth AXI GPIOs. The R5 application reads the state of second push button in polling mode. When it is held, it toggles the second LED and prints "Hello World" to the terminal. DDR allocation. One common mistake when running two cores in Zynq devices is failing to adjust the DDR memory addresses in the linker scripts to ensure each application uses its own memory region. By default, the linker scripts assign the same base address to both applications, with the memory size determined by the hardware platform's available DDR. If left unchanged, both the ARM0 and ARM1 applications will attempt to operate within the same DDR address space, which will cause conflicts. To resolve this, the DDR memory regions must be divided so that each core operates in its own space. For simplicity, I divided the DDR memory into two halves, the lower half for ARM1 and the upper half for ARM0. Since these are bare metal applications performing minimal tasks like printing a single line to UART, they don't require much memory. ARM1's base address was left at its default value, but its size was reduced to 1 gig, half the available DDR. ARM0's base address was set to start immediately after ARM1's allocated region, and its size also set to 1 gig. Build the project. With both applications configured, build the entire project. Once completed, you have the A53 application running FreeRTOS and the R5 application running as a standalone program. You can find that the second ELF file is also created to run on the R5. Launch the project on device. With our software built, it's time to run it on the actual hardware. First, let's connect our ZCU104 board. We'll need to connect the power supply, the JTAG USB connection for programming, and the UART USB connection for console output. Using the Launch hardware feature in Vitis, We'll load our Bitstream on PL side and 2 applications onto the ARM cores. Once the applications are launched, both ARM cores output their respective messages to the serial terminal, confirming that the 2 applications are successfully running on the targeted ARM cores. Subsequently, the ARM cores begin monitoring the push buttons. When the first push button is pressed, the A53 core starts blinking the first LED and prints "Hello World" from A53 to the serial terminal. Similarly, when the second push button is pressed, the R5 core starts blinking the second LED and prints "Hello World" from R5 to the serial terminal.